Alright, so we're going to be talking here about the electron in the atom, probably the most important particle. 95% of all the chemistry we'll cover in here has to do with the electron, sharing electrons, giving, taking, transferring. The flow of electrons is electricity. The only part that we really focus on the nucleus is nuclear chemistry, and that'll be towards the end of the year. But so the first thing we need to do is know where the electrons are in an atom. In a little bit, it'll be more specifically where those outer electrons are, the valence electrons. But for right now, the electron configuration, the arrangement of the electrons in an atom, is what we're going to be looking at. There are three main rules that dictate these electron configurations. First is Aufbau's principle, and this says that electrons are going to fill orbitals that have the lowest energy first. And remember, that is going to be closest to the nucleus. And this is what we talked about with the modern atomic theory, the fact that atoms want to be in their ground state, the lowest energy position. And so that's why the electrons will be in those places, most likely found in those places first. Next we have Pauli's exclusion principle, thanks to Wolfgang Pauli, yeah. And this says that orbitals can have a maximum of 2 electrons in them, and if there are 2 electrons in the orbital, they must be spinning in opposite directions. Remember that electrons have the same charge, and like charges repel. So, in order to be in that tiny little orbital together, they have to be spinning in opposite directions in order to create oppositely charged magnetic fields. So that way they can be in such a small space together. So the electrons are going to be closest to the nucleus in the lowest energy positions, and if we can have up to 2 electrons in each orbital. The third rule, Hund's rule, courtesy of Friedrich Hund, it says that orbitals on the same energy level, on the same energy sublevel, are going to be occupied by 1 electron before we pair them up. And I'll show you how that looks when we get into this in a little bit. So here we have the first look inside the atom. So you'll notice down here it says nucleus, so the nucleus is there. And on the side we see that energy is increasing as we go away from the nucleus. Hold on one sec. Sorry, I had to cough. But what we see here is that for each energy level, there are sublevels. So energy level 1 has 1 sublevel. Energy level 2 has 2 sublevels. Energy level 3 has 3 sublevels. Energy level 4 has 4 sublevels. And you'll notice that these sublevels have those letters of the orbitals we were talking about. S, P, and D, and F. So basically what we have here is what I like to say is like an electron hotel. Inside the atom, we have the electrons in orbitals, which are on sublevels, which are on energy levels. So it's like a hotel. You have rooms in hallways, which are on floors inside the big building. Okay, so that is just one look inside the atom. And so if we look at the next view that I created for you, and hopefully see that this makes a little more sense. It's not the Holiday Inn, it's the Electron Hotel. Alright. So again, down here we see the nucleus. And as you go away from the nucleus, again, there is increasing energy. And so we see that we've got our sublevels, and on the sublevels you see I have these circles. Well, what these circles represent are the orbitals. And they have the S, P, D, and F notation again. But, I can't draw those, so we'll just use circles for the orbitals. And so what we need to do is figure out the electron configurations of the different atoms. Where are the electrons most likely to be found? Well, let's start with our good friend hydrogen. Hydrogen, our simplest atom, has one electron. So what is its electron configuration? Where is that electron most likely to be found? Well, it's not going to be way far away from the nucleus. It's going to be close to the nucleus in the lowest energy position possible. And so that is down here in the 1s sublevel. And I draw a little arrow to represent that there's an electron there spinning clockwise. So the electron configuration for hydrogen is 1s1. And so to a scientist, that notation means, hey, there's one electron in the 1s sublevel. So what about helium? Well, helium, our next simplest atom, has two electrons. So the question is, where is that second electron most likely to be found? It's going to be down here somewhere. Is it going to be in the 2s or in the 1s? You might think the 2s, but actually there is room in that 1s sublevel because we can put two electrons in each orbital. So the electron configuration for helium is 1s2. Okay. So let's jump up a little bit. Let's go to nitrogen. Nitrogen has 7 electrons. And by the way, how do I know this besides just being awesome? It's the atomic number on the periodic table. Remember, the atomic number tells us the number of protons, and since all atoms are electrically neutral, it tells us the number of electrons as well. So nitrogen on the periodic table, number 7, 7 electrons. So starting down here at our low energy position, I know that I can put 2 electrons in the 1s sublevel. Next up is the 2s sublevel, and I can put 2 electrons there in that orbital. After that is the 2p sublevel. And yes, I can visually see it down here at the bottom, but you're going to really want to know and pay attention to this order of filling up here at the top. You will not have to memorize that. Perhaps if you go a little further in chemistry, you will. But for right now, this order of filling shows you the sublevels in the order that they get filled up based on their energy. Because, as you can see here, after 3p comes 4s. Okay? Because there is some overlap, because the atom is so incredibly small inside, that we're going to have overlapping of the sublevels based on their energies. So, going back down to my picture, I can see that the next electron is going to be on this 2p sublevel. So that's where the 5 electrons are, and there's only 2 more that we need to figure out where they're going to be. And this is where we see Hund's rule. Hund's rule says, okay, when you've got orbitals on the same energy sublevel, we're going to put an electron in each of them before doubling up. It's kind of like if you were at a hotel. It's much better, it's much more relaxing to have your own room than to have to share a room. So from an energy situation, it's much better to spread the electrons out, so my 6th and 7th electron are going to end up there. And so the electron configuration for nitrogen, in the 1s sublevel we have 2 electrons. In the 2s sublevel we have 2 electrons. And in the 2p sublevel we have 3 electrons. Electron configuration is kind of like electron accounting. Where are the electrons? And when you're a good accountant, you always double check your work. And so with electron configuration, the exponents, 2 plus 2 plus 3 equals 7. And those exponents for our electron configuration will always add up to the atomic number of the element. So, do we want a little shortcut, something a little simpler to do this? Well, let's check that out here. In order to make this a little simpler for us, we need to really understand a couple things on this diagram. First off, again, that the circles represent orbitals. Now next up, for every s sublevel, you will notice going up the side 1s, 2s, 3s, 4s, etc. Every s sublevel has one orbital. So what that means is every s sublevel can have 2 electrons maximum in it, because that is our occupancy per orbital, 2 electrons per orbital. For every p sublevel, you'll see that we have 3 orbitals. So with 3 orbitals, that means 6 electrons maximum in every p sublevel. D sublevels, you'll notice that there are 5 orbitals, giving us a 10 electron maximum. And that leaves F sublevels, where there are 7 orbitals, 14 electrons maximum. You need to know those numbers. S has a 2 electron maximum, P has a 6, D has a 10, and F has a 14. So knowing that, and knowing our order of filling, we can easily do an electron configuration. Phosphorus has an atomic number of 15, so we need to configure 15 electrons. First up on our order of filling is 1s. S can have 2. That's full, move on. Next up is 2s. 2s can have 2. That's full, move on. Next up is 2p. P can have 6. So when we put 6 in, 2 plus 2 plus 6 is 10. So we have 10 down, 5 more to go. So again, 10 down, 5 to go. So after 2p is 3s. 3s can have 2. That makes 12. Next up is 3p. 6 is the maximum, but I only need 3 to get to the 15. So that is the electron configuration for phosphorus, following the order of filling and using those guidelines for the maximum amount in each sublevel. Pause the video and see if you can do calcium, whose atomic number is 20, and niobium, whose atomic number is 41. Hopefully you pause the video and you can check to see if you got those answers for calcium and niobium. Again, just following the order of filling and using those numbers of 2, 6, and 10 for S, P, and D. F is 14, that's reserved for some bigger elements, which you'll get on that practice sheet. So the last thing here, what if I gave you an electron configuration and you needed to tell me what element? Well, it's just a matter of adding up the exponents. So for this first one, 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 1 equals 37. And when I look on the periodic table, that's Rb, rubidium. So pause the video and see if you can do the next one. Hopefully you paused. 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 6, 26. Iron. So that is electron configuration. Hopefully the practice goes well, and I'll talk to you about the light aspect of electrons in our next video.